Get rid of all my other windows here. All right, so Josh tells me we've hit a critical mass, which is great. So welcome everyone to yet another Radio Shop chat sponsored by SpectrumX. I'm Nick Lanneman. I'm Center Director of SpectrumX, and we're really excited to have all of you here with us today, but also really excited to have today's speaker, Alex Damnjanovic from Qualcomm. Just a few quick reminders before we get started. So SpectrumX is the world's largest academic hub that's trying to address all sorts of issues around research, education, workforce development, and collaboration around the radio spectrum. It's a very exciting program. And one of the things we do to facilitate that is to organize these, what we call radio shop chats. So you want to imagine being in the radio room with the old experts that know how to tune the radios up and avoid interference and so on. We're trying to generalize that. One thing that I just want to stress about our process for these chats is that we try to keep open discussions, and to the extent possible, though, we try to follow the so-called Chatham House rule. And what that means is we're really trying to have a vigorous debate and also some tutorials about various spectrum issues. But we do record the session for internal purposes within SpectrumX. But we ask that what you learn here, you don't attribute to anyone in particular as you go forward and make use of the information. The last thing I want to stress is there's lots of opportunities to get involved in SpectrumX. We have a mailing list. We do a fair amount of outreach using LinkedIn, and also our website, which updates and provides updates on all the things that we're up to. So please get involved if you're not already fully connected and involved already. With that, let me just go ahead and introduce Alex as our speaker. Again, Alex is at Qualcomm. Alex did his PhD at George Washington University, and then moved out. I guess he got tired of the East Coast, so he went out to the West Coast. Who can argue about San Diego? Started with Ericsson, but has been with Qualcomm for 20 years now. And so we're really excited to have Alex here. Alex has led the charge to have Qualcomm join SpectrumX as one of our first collaboration advisory board members. And so we're really happy to have Alex here to give us some updates on what Qualcomm is up to in the Spectrum ecosystem. And with that, I'll pass it off to you, Alex.
Thank you, Nick. Thank you for the introduction, and thank you everyone for giving me this opportunity to present our research. So let me share the screen. Do you see what I'm sharing?
Yep, coming through great.
So today's talk is going to be about new technology that we are working on that would be applicable for the future wireless networks, even the existing one, with the goal of improving the spectrum use. So, okay, so now I'm trying to go to the next slide. And okay, so it worked. So today's agenda, I'll first go over the global 5G deployments. Then I'm gonna discuss a little bit about why we need more spectrum for the future wireless networks. And then we're gonna talk about new spectrum sharing techniques or technologies. I have about 29 slides, and I would like to go over all of them, but if you have any questions, feel free to interrupt me. The focus of the presentation will mainly be the third part, but just to set the stage for that discussion, I want to also go over the 5G deployments and the need for more spectrum. So global 5G deployments are well underway, utilizing low, mid, and millimeter wave spectrum bands. They're driving digital transformation across industries. I mean, various use cases: transportation, manufacturing, industrial, entertainment, public safety. And then the estimate is that there would be that 5G will enable 13 trillion in global sales activity in 2035. 5G continues to expand globally. We have 245 or more operators with 5G deployed commercially, and then 270 additional operators investing in 5G. There are more than 1 billion 5G connections globally, and we have more than 6 billion 5G smartphones that will be shipped between 2020 and 2026. And at this point, there are more than 1,800 5G devices that are launched or are in development. So 5G can operate in all types of spectrum and bands. We have low band, mid band, millimeter wave spectrum. It's also licensed, exclusively used spectrum. Then unlicensed spectrum, 5G can operate in unlicensed spectrum as well. And then we have the shared spectrum. We don't have that many different, I should say, paradigms right now, but the new ones are coming. And I'll go over that in the second part of the presentation. What's important is that spectrum is the lifeblood of wireless communications. So without spectrum, there would be no wireless communications. When it comes to 6G deployments, this slide summarizes what is currently allocated or targeted by 5G. These are mainly 5G, these are spectrum bands for MNO deployments. But in addition to that, there are also spectrum allocations optimized for industrial IoT, various verticals, and private networks. And this slide summarizes that. When it comes to then future networks, more spectrum is needed to enable future wireless growth. As I just mentioned, spectrum is the lifeblood of future wireless innovation. And we need more spectrum for future applications. So when it comes to spectrum, it is important that ITU continues a spectrum pipeline ensuring the continued 5G growth across regions and enabling future 5G advanced and 6G use cases. And illustrating here the key agenda items on the upcoming World Radio Congress, Conference 2023. There are certain agenda items that are dealing with spectrum applicable for current deployments, but also plans about future 6G bands. That would be agenda item 10. That would be basically proposing topics or agenda for World Radio Congress 23. And what we believe is that it is important that that World Radio Congress addresses this upper mid-band in all 6G regions. And when we talk about upper mid-band, we are referring to 7 to 15 gigahertz range. And I'll talk a little more later why we think this is a very important range for 6G future networks. So the other part of the 6G development is the status in 3GPP. As you can see from this slide, 3GPP workshop is anticipated to occur in 2025, where after which the release 20 study item will start. This is basically the process in 3GPP where first the technology is studied, and then after that study item is completed, then what's agreed in 3GPP will be standardized in the following release, which could be release 21 and after. So that's where basically we can expect these new networks or 6G to be deployed. And as you can see, the anticipated timeline is that this starts in 2027. So it is very important that at that time there is some clarity from the spectrum allocation perspective. World Radio Conference 2027 start addressing the spectrum issues. So that was about basically spectrum and 3GPP development status. Now, when it comes to 6G, there are new use cases that are being discussed in the industry right now that will be part of 6G. There would always be a fixed and mobile broadband evolution, but then there are other applications such as critical services that are enabling intelligent transportations, enhanced XR experiences. There would be a lot of verticals. There would be the sensing. Sensing is, integrated communication is sensing is also expected to be a part of 6G. Ultra-wide connectivity, and many unknown future use cases that will become clear in the future. And for all that, we basically need more spectrum. And when it comes to spectrum, it is, as I mentioned, we have all. We have a licensed, unlicensed, and shared spectrum, and it is anticipated that 6G will operate in all of them. Licensed spectrum is always the exclusive license is always the industry top priority, and if that is feasible, that is always the best case. However, if that's not feasible, then what we are looking at is at new technique or innovations how to keep the benefits of licensed spectrum, but do it in a more efficient way through sharing. So basically, we are looking at ways to ensure quality of service can be guaranteed in the same way as it is done in a licensed spectrum, and still allow shared or more efficient use. So in terms of how much bandwidth is necessary for these 6G networks, what is shaping up as a common industry view is that wide bandwidth is important. So basically 500 megahertz of contiguous spectrum allocation is what the next generation wireless systems are looking at. And then in that regard, this upper mid-band is a suitable range to find a new spectrum that provides the right amount of capacity and coverage that these new applications will need. I already started touching upon it. So basically, we are targeting 500 to 1 gigahertz of licensed spectrum per operator for 2030 and beyond. We need contiguous bandwidth to basically of at least 500 megahertz to achieve the benefits of 6G. 6G will deliver new capacity for wireless broadband, and it will fuel scalable XR, and then it will support high resolution RF sensing for new use cases. As I mentioned, we are focusing on the upper mid-band or lower 9 gigahertz of that, because upper mid-band actually refers all the way to 24 gigahertz. So we are focusing on the lower part due to better coverage and still good capacity coverage trade-off. So the idea is that we utilize upper mid-band and so that spectrum can now be deployed at the same location where we currently have macros deployed, so MNOs can deploy that and use advanced technology to ensure that the coverage is comparable. So so that's the key, that why we are looking at this upper mid-band, because we are looking at the right capacity coverage trade-offs. With that, I mean, there is always the option for densification, but in the trade-off in terms of how many sites are deployed and how much spectrum is utilized, this upper mid-band is shaping up to be the optimum spectrum for 6G. So in addition to upper mid-bands, we believe 6G will also utilize sub-terahertz spectrum. However, those are mainly specialized use cases, such as wireless fronthaul, wireless fiber to home, and this type of applications where we do not need basically macro coverage for mobile broadband due to propagation losses. It's simply not practical to deploy that frequency at the existing macro sites and expect coverage, or to densify the network to such an extent that this frequency can be used for cellular service. So then what we are doing is we are looking at ways how to improve how efficiently the spectrum is utilized. So we are looking at various scenarios and techniques, all within what is currently basically happening in industry and trying to take it to the next level. So as I mentioned, we are looking at licensed spectrum, unlicensed spectrum, and shared spectrum, and all of those will provide our view of what can be done as a next step towards increasing efficiency and utilization, basically, of spectrum. So a brief summary of what has been done in unlicensed spectrum when it comes to 3GPP technology is that in the last 10 years, 3GPP and Qualcomm work on enabling 3GPP technology to operate in unlicensed spectrum, and NRU, which is standardized in release 16 of 3GPP, allows deployment in unlicensed spectrum. It started with LAA in LTE, and then we have now NRU, which is it's operating both in standalone mode or in license-assisted mode. Then we also have, at the moment in the US, we have also sharing of spectrum with government incumbents, and that's 3.5 gigahertz CBRS spectrum. We have a three-tier shared spectrum paradigm where a spectrum access server is utilized to ensure that incumbents are protected. And it's fair to point out that this method is fairly slow in terms of how coexistence works. So in terms of protection of disabling use of spectrum based on the presence of incumbents, which are mobile, it's fairly long term. It's in the matter of hours. And there is obviously an issue here if the spectrum becomes, utilized, then we have deployments, and then the incumbents come in. It basically blocks the entire spectrum, so there is no communications. So now I come to the basically core of today's talk, and that is what we can do to improve spectrum sharing, what we can do to improve utilization and reduce spectrum cost. And basically, we noticed that as we keep increasing these the frequencies where we are looking for deployments, we have the in case of particularly upper midband, the antennas. We can fit larger number of antennas in a given antenna aperture, to the point that this what we call giga-MIMO technology can be very suitable not only for increasing the capacity through various types of multi-user MIMO scheduling, or even simply high directivity communications and improving the link budget. But the same technique can be used also for sharing because of the focused beams. Even though we will be utilizing upper midband, the beams are becoming as narrow as what we have in millimeter wave. And in millimeter wave, basically sharing comes as basically a first comes to mind how to utilize millimeter wave in high frequencies is that a lot of that spectrum can be shared because of directionality. So that's basically the first technology that we believe it's suitable for sharing, and that's GigaMIMO. The other aspect is that and I'll go more into the details, is that now if we allocate spectrum to multiple users, but those are basically still licensed users for that band, they can find ways how to coordinate and share spectrum. Again, talking about spectrum when we have narrow beams, there is basically an opportunity for spatial coordination between transmissions. Then, of course, there is always AI/ML that can address coexistence in many cases, and one reasonable use case would be how public networks can share spectrum with private networks. And then finally, the latest development in O-RAN is that by opening the front haul or by standardizing the front haul, there are a lot of opportunities how the networks can be deployed and spectrum shared because of the fact that the link between the antennas and the remaining part of the network, so-called distributed unit, if it's open, then that creates a lot of different options how the networks can be deployed. And the main idea there is that the spectrum should not be left unused. So even if spectrum is licensed for someone, if it's not utilized, others that need spectrum can be used, provided there is a proper monetary compensation. So I touched upon GigaMIMO. So in case of GigaMIMO, we have in sub 7 gigahertz, we typically have 256 antenna elements at the base station, and that's illustrated here on the slide. In case of upper midband, now we can start fitting more antenna elements into the same aperture, and that the fact that we have more antenna elements can be utilized to provide beamforming gain that, as illustrated on the right-hand side, can basically create similar coverage when it comes to, at least in this example, we see that in our tests near our Qualcomm campus, we see that these larger number of antenna elements were sufficient to provide comparable coverage between the two frequencies. But as I mentioned in the previous slide, these GigaMIMO technology does not need to be utilized to provide comparable coverage or enhanced capacity. These narrow beams can be also utilized to coexist with incumbent systems or the systems that are already using that spectrum, no matter what their incumbency is. So basically, the benefits, the spectrum sharing techniques that we see in millimeter wave can now propagate into upper midband, and we can basically have the best of both worlds in terms of capacity and coverage and coexistence with other technologies. Which specific mechanism we can use depends on the target band and the incumbent systems. What is illustrated here is how terrestrial deployments can coexist with satellite uplink or satellite space to Earth to space direction. So basically, all we need to do is to make sure that at the base station, the beamforming is such that in the direction of the satellite, the ERP mask is met, so that that type of interference can be tolerated at the satellite receiver. Obviously, the exact numbers will depend on and actually depend on the satellite system deployed and on basically the capabilities of that receiver and the power that we can use in that band. But the point is that when it comes to these technologies, that these narrow beams can be useful not just for the system itself, but also beneficial to others as a way of interference management to other system or protection. So that's basically where we are coming from in terms of where GigaMIMO can be utilized for sharing. Now, continuing in the theme of utilizing narrow beams, Qualcomm, we had a proposal for to FCC for sharing in lower 37 gigahertz band, where we proposed something called coordinated spectrum sharing based on sensing. But the idea is, I mean, it's general. It doesn't have to just apply for 37 gigahertz band. It can apply in all bands when we have relatively narrow directional transmissions on narrow beams. And the idea is to basically exploit spatial multiplexing, but also at the same time guarantee service. So we illustrate here on this graph is utilizing on the x-axis high quality of service as a metric, and on the y-axis network capacity. What will happen with uncoordinated sharing for the two operators? So basically they don't do any sensing, nothing. They just transmit because they use narrow beams. Likelihood of collisions is small, but nevertheless it occurs. And when that happens, we have the interruption in service. So what we done here, we looked at how much or how often that interruption happens and when it becomes unacceptable. And what we've seen is that in this particular example, we saw that even in 37 gigahertz, when we have narrow beams, 70% of the users had okay quality of service, but 30% did not. So then we tried to come up with a approach that would enable sharing with a quality of service guarantee. And when we have a shared spectrum and not a licensed spectrum, when the number of users or deployments is uncontrolled, we can develop a scheme that relies, in this case, on synchronization and sensing, so that each operator, in this case, or a user, we can call it, gets its own priority channels. But then it can utilize all other channels or channels of others if it determines that through sensing that channel is unutilized. And for that reason, we basically exploit the synchronization or the time component for coordinated spectrum use. So basically, what we are saying here is that when it comes to advanced sharing techniques, we should not be just limited to using different frequencies and narrow filters, but also try to exploit time component and spatial multiplexing when it comes to sharing. And then if we have this framework where every user has its own priority assignments, then there is no issue in terms of quality of service where the spectrum is unavailable. The spectrum is always available and on a priority basis, and it would be up to the other user to quickly determine whether the spectrum is free, that secondary spectrum, and when it can be utilized and when it can basically need to be vacated. And for that we have here illustrated how this mechanism would work. And that is basically showing that two communications link can occur in parallel on both channels, in this case, two operators, two channels, if the users are not in the proximity of each other. So the two networks can determine based on sensing in a technology neutral manner, because all we have done here is do sensing based on time, specific time occasions, and based on energy. When these communications links are effectively orthogonal, even though maybe occurring in the same geographical region, but just due to narrow beams, basically spatially separated, when the communications can occur on both channels, and when it cannot. So what we assume here on the first figure on the left, top left, is the two communications links are spatially separated. As users move, then basically through sensing, the networks detect that and basically fall back to a single channel, which is the third figure on the bottom left. So we are going left to right and then top to bottom in terms of the figures. So as we can see here that this type of mechanism dynamically adapts to user locations. So it supports mobile service, and it could be implemented with a simple sensing rules, simpler than what we currently have in unlicensed spectrum. The reason why in this case sensing like what we have in sub-7 GHz spectrum is not proposed is that when it comes to directional transmissions, it's very important that the receiver is detected and not the transmitter. And this sensing operation and synchronous sensing operation allows so-called victim users to send energy at specific instances so that their communication links can be proactively protected. So the last figure shows that when two users move, then communications on two channels can occur. So again, we are stressing here that when it comes to higher frequency bands, which I would argue even upper mid-band could represent that for some cases, then these directional transmissions can occur simultaneously over the same geographical region. So that is basically the technique for sensing and sharing the spectrum based on directional spatial techniques, utilizing also synchronization or time components in order to understand when each deployment is supposed to sense the video. Another area that we are looking at for sharing is how to leverage ORAN for improve the sharing. In this case, we are not talking about sharing between different deployments. In this case, we are talking about reusing part of the deployment, but in this case, this would be shared ORU, and the rest of the network does not have to be shared. That actually differentiate this approach with RAN sharing that is standardized in 3GPP since at least I remember release 8 for LTE. So the idea here is that to basically leverage open front haul to rethink how networks can be deployed and spectrum can be allocated. As we know that if we have exclusive licensed spectrum, then we have to statically partition the spectrum as shown on the right figure on the top, and then the user experience is limited with the spectrum that is allocated. Now, with spectrum sharing, in the figure on the bottom, we illustrate how that service time can be reduced, up to half, because if two operators share the same spectrum, if one of them only has traffic and the other doesn't, then the one could, in theory, use the entire spectrum. And that's illustrated here. The key here is that how to prevent collisions and how to ensure that when one MNO needs spectrum, it actually gets it. So what we are proposing here is that similarly like what we had for the advanced spectrum sharing framework, we enable dynamic reuse of spectrum through allocation of so-called primary allocation for each MNO, that it would always have that access to that spectrum guaranteed, and ensuring that there exists a mechanism for the other MNO to vacate that spectrum quickly, so that the primary operator always has this access to its own spectrum. And that's basically where this shared ORU comes in with open front haul, is that then this shared ORU can be used just as a way to share equipment, and these basically radio units sites, so that would significantly reduce the capex and opex of the operators. That already actually even now exist when tower companies provide sites to the MNOs. In this case, they could also provide the shared radio unit, but the spectrum could be exclusively licensed to each MNO and not shared. But just looking at this architecture, one can ask questions, but why can't they share the spectrum as well? I mean, the knowledge of which MNO is using which spectrum is actually at the shared ORU. It's not that shared ORU need to be very smart in terms of allocating the spectrum, but one can basically come up with a very simple policy where shared ORU is simply relying information and allocating spectrum based on that policy, which operator is using which spectrum. That actually itself facilitates this fast use of spectrum, because the requirement on this ORAN architecture anyway is that this open front haul for the interface that is standardized, the so-called 7.2 split, has to be pretty low. So that requirement for that protocol split between the DU and the ORU provides opportunities for fast reallocation of spectrum resources between the MNOs that share that ORU. So all we are saying here is that we can leverage that work, and that is actually open front haul is standardized in ORAN. They're working on different iterations, and even the shared ORU is a work item there. And we already had discussions in NGRG group of how to enable this framework in the future networks. It's not that really any new interface is required. 5G could be deployed in this way. It's all about open front haul that, as we will show later, the next slide provides new opportunities. So, so the sharing of spectrum is one aspect. But also there is, this type of deployment can also save power, or it can meet sustainability goals. And in general, access to the spectrum becomes easier, because all that is necessary is to support this open front haul, and then different ORUs can be shared. And then the owner of the shared ORU may actually even monetize from the leasing of that spectrum on a very dynamic high scale basis. Every millisecond spectrum can be allocated to the highest bidder. Whoever wants to pay the most at that point gets the spectrum. And if it's completely unutilized, I assume that the highest bid will be pretty low, which can reduce some some issues with in terms of cost of the access to the internet. And overall, the quality of service here can be controlled very well because there is always priority spectrum, and the latency to get that spectrum is very small because basically it should be even transparent for the priority user. It's more about the other user who needs to deal with uncertainty about spectrum availability, which is even less uncertainty than what is currently implemented in Wi-Fi, where we base or unlicensed any unlicensed spectrum technology, that where through sensing we never know when the spectrum will be available and then be ready on a very short time scale basis to access that spectrum. So basically, this open front haul, in our view, is a major opportunity to develop new framework how we can deploy future networks and how spectrum even can be utilized. And some use cases are illustrated here. I'll try to address them to some detail, but feel free to follow up with questions if you don't have time today, maybe after. So the first one is simply shared ORU, where multiple MNOs deploy their DUs, as illustrated here, virtualized with cloud implementation, and then the front haul to the ORUs that are shared. So these shared ORUs could be owned by tower company, or they can be jointly owned by MNOs. They already, in many cases, share sites anyway. And they can partition their resources on a priority basis where they have priority access, but then it's very easy for them to reuse each other's resources when they are not utilized. The other option is that let's say dedicated ORUs, but it's also shared in a way where each MNO deploys its own ORU on its own spectrum. And then each MNO allows other MNOs to access their shared ORU and their spectrum when it's not utilized. So they can both benefit either monetarily when they don't have traffic, or if they have high QoS traffic, or traffic that cannot wait, then they could potentially use other ORU and serve that user there. The third approach is hybrid, where this deployment may work only on a specific channel. So each MNOs can have its own ORU, and that ORU can serve certain frequency and certain users there and not be shared. So that doesn't have to be shared. That is basically the current framework. But then there could be another ORU deployed, either owned by these MNOs jointly or by a third party, and they can share it. So that is what we call hybrid in this case. Now it's the variation on the same theme, but now even these ORUs, they could even be deployed indoor, they could be part of private networks. And as long as this front haul interface is open, then the MNOs may be able to access other networks, but not the entire network, just the radio units, or just basically the antennas, and ensure that the user has its own experience, so that there is no change in networks. It's still the same network. It's just that the hardware that is utilized is hardware that is utilized by the network that was basically private deployment. And last but not least, if we have this open front haul and the ability to share ORU and spectrum, this sharing can also work with government users. So the government users can adopt, or priority users can adopt and share these ORUs and prevent others from using that ORUs on a very high, very fast scale basis. Here we are talking about millisecond level sharing because because the whole framework works on that time scale. So we don't have to have like what we currently have in CBRS, network outage that lasts for hours or even longer, but rather we can gradually develop the sharing techniques that allow more dynamic or sharing of even in time or part of the band that is tailored towards specific incumbents that the network can already handle because of the whole open front haul and the sharing of radio units and the spectrum. So basically this sharing with government users, if they have the ability to access to support open front haul and access the radio unit, they could create their own patents. They can have their own DUs and not basically access the network through other MNOs DUs if they prefer. So those are all possible deployments that this open front haul and shared ORU framework would allow. And last but not least, we also believe that unlicensed spectrum can be access or efficiency of unlicensed spectrum can be enhanced. We currently have for 6 gigahertz, we have the contention-based protocol that provides rules to protect incumbents and also regulate medium access. Actually, I would say that it's mainly to regulate medium access, but it does have benefit on the incumbent protection in 6 gigahertz in the US. What we are saying here is that we can add a new access mechanism. I shouldn't say fairly drastically new, but if we rely on synchronization, we can implement the existing access mechanism in a synchronous manner and improve coexistence between different technologies and enable so-called multi-point transmissions that would lead to another level of efficiency of network use. Because when we have dense deployments of nodes, what this asynchronous access would achieve, it will basically prevent certain nodes that are nearby to access asynchronously the same spectrum. But when we have synchronous contention, if those nodes are from the same deployment, they can synchronize their access and improve efficiency. But what is important then is to ensure that these new synchronized schemes can coexist with the existing systems that are utilizing asynchronous access. And our view is that introducing this synchronization in terms of accessing mechanism can be beneficial even for unlicensed spectrum, where we want to basically reuse that spectrum more efficiently in order to support higher data rates that are also expected for unlicensed spectrum. And that's basically wrapping up the presentation. Just to go over the conclusions, the global 5G deployments are well underway, utilizing low, mid, and millimeter wave spectrum bands. When it comes to cellular networks, more spectrum is needed for future wireless growth. And these new sharing techniques can open new spectrum. And in these new sharing techniques, we are looking to exploit spatial components, time also. And these new technological innovations can realize new levels of efficiency and utilization of spectrum, both in case of these network enhancements, but also radio interface enhancements. And that would conclude my talk. I think we have about 10 minutes left for questions.
Thank you, Alex. Yes, we do have about 10 minutes. And if I'm monitoring the chat, I think Mike Honig had the first question in the chat. Is Mike still with us?
Yeah. I assume you can hear me. My video doesn't start. So you talked a fair bit about synchronization. So I'm wondering, first of all, to what level of synchronization are you talking about? Frame level, symbol level, time slots, and do you need, or rather, so how does synchronization and TDD fit into your vision of GigaMIMO? I mean, is this something, clearly TDD is easier to do joint optimization of precoders and receivers and so forth. So do you see that as being of, or how important do you see that?
So I guess the first question is about synchronization, level of synchronization, right? So when it comes to synchronization for medium access, that is fairly different than synchronization for example, distributed MIMO or coherent comp. So synchronization here is simply synchronization to ensure that we don't have a collision. And in case of these advanced sharing techniques that we refer within same technology, or I shouldn't say same technology, shared spectrum, where we don't have to contend, then the synchronization is basically on a OFDM symbol level or slot level, where it is clear which party is supposed to sense the medium to detect presence of ongoing communications. So that's fairly low requirement for synchronization. When it comes to unlicensed spectrum, synchronization should be only within whatever the sensing slot is. So in case of unlicensed spectrum, 6 gigahertz, sensing occurs over 9 microseconds. And actually, even that 9 microseconds is split within sensing period and turnaround. So anything within a microsecond will not be noticeable in terms of the synchronization error for sensing. So that's when it comes to what level of synchronization we are looking at in spectrum sharing. So it's simply to look at to avoid collisions, to avoid transmissions at the same time, or undesirable transmissions. And when it comes to you mentioned about TDD spectrum,
Well,
you were referring probably about the channel feedback and ability to do practicality of feedback if it's not TDD spectrum and things
right.
of that nature, right? So yeah, I mean it's definitely more feasible in terms of channel feedback, although we are looking at also techniques of half-band duplex, where we have concurrent transmission in order to link budget. But I think your question is more of the matter of channel feedback and TDD versus FDD.
Right. So my follow-up is how important do you see, how do you anticipate doing the beamforming in, say, 37 gigahertz with lots of antennas? Do you have in mind FDD with channel feedback, or do you have in mind?
Yes, right. 37 gigahertz. Our proposal is for TDD, so it's basically using the millimeter wave. It's actually supporting current release of 3GPP. So it's not any new technology. It's simply utilizing the existing waveform to enable sharing of spectrum and use of the wider bandwidth. It's not FDD frame.
Thanks.
In the interest of maybe capturing at least a few more questions, I don't know if you've monitored them all, Alex, but I think Chris Dupree was next up.
Mm-hmm. With passive users, that's a very good question. We basically cannot sense. So what we are talking about is we need to know the location, time of use. So I mean, one option is whether this radio astronomy can also benefit from synchronization in terms of time when this would occur and for how long. We had that discussion in XG Alliance. I think Onisha brought it up, and it is part of that technology report. But yeah, I mean, it's not possible to sense, so we have to make sure we limit transmissions in that directions where narrow beams help. And in terms of why we need contiguous spectrum of 1 gigahertz is that every new technology basically relies on wider and wider bandwidth, and it's more economical to have a single waveform contiguous band versus carrier aggregation. So that's where we come to, we mentioned at least 500 gigahertz, 500 megahertz. That will be the leap that every G makes between 2G, 3G, 4G, 5G, and to support more capacity. So basically, it's the economics and more capacity. Hope I answered that question. In terms of the ARP level of the 37 gigahertz band, it would be no different than any other millimeter wave band, and it's basically it's less than 40 dBm. In terms of the total ERP, the conductive power definitely is no different than what we have in the lower bands. Where does 9 microseconds threshold for the sub 6 gigahertz sensing come from? That comes from the current actually ETSI standard that is widely adopted in the industry across the world to access the medium. So that protocol also standardized in IEEE Wi-Fi standard, but part of ETSI and also part of 3GPP is that 9 microseconds is the sensing slot, and there are multiple 9 microsecond slots, and eventually the node transmits, but it is necessary to quickly turn around in order to avoid other nodes to access at the same time. And that is the requirement that unlicensed networks are capable of. And what we mentioned about ORAN is that if we apply that same requirement to cellular networks, we have new opportunities how to share spectrum utilizing ORAN.
All right, we may have time for one more question before our nominal end time at 4 Eastern. If no one else has a question, I might be able to throw one out there.
Mm-hmm.
All right, here you go. Oh, sorry, go ahead.
Can I ask, Aleksandar? Actually, one thing I have as a question is your vision of sharing is based on the idea that when it comes to operating in any particular location, operators have an interest in playing nice with each other and having everything function. Do you think that's true? Or do you think local operators could use these networks have to be built to defend against incentive incompatibilities and operators potentially using them to degrade each other's service?
Right. So that's a good point. So what we want to make sure is that there is a framework in place, both in terms of technology and regulation, that would motivate constructive interaction for the good of all, as opposed to making sure that we are incentivizing negative, basically, not positive cooperation, but rather incentivizing MNOs to hurt each other. So what is true is that if that's the case, that would lead to a lot of spectrum being unutilized, because then it's more about the fight to secure spectrum. Problem now is that we don't have any spectrum left that is suitable for cellular deployments. So we should think in a new way how to incentivize better utilization of that spectrum and still motivate the basically competition. making sure that there is differentiation between MNOs, that they can provide that, so that basically that competition drives innovation. Our presentation is along those lines, that this new technology can actually change this deployment, so that MNOs can actually cooperate, and yet both benefit, or not both, but everybody that is cooperating can benefit.
And it's come to my attention that Dan Lubar might have several questions, but Dan, do you want to sneak a quick one in here before we wrap up?
Sure. I'd love to do that. Thank you, Nick. Here's a really quick question that was asked sort of in the context of 6 gigahertz and below. I'm sort of curious to nail down GMIMO a little bit in the context of OFDMA and TDD, and how both of those methodologies to access, sense, and use the medium are done. Are these sort of proprietary solutions for your company, or are these really hard and fast standards that people are working under? And do you think there's a lot of alignment in industry around this process of getting access to media, sensing, and sharing? Just as an example, your example earlier in the talk about how you were getting in 37 gigahertz, maybe you had 30% of the folks weren't getting on. How in that kind of situation are you, in a standard kind of way that everybody might agree on, being able to get access with those other bands that you'd love to try to use instead?
Right. So there must be, thank you for the question. So it must be a rule. We are not talking about proprietary solutions. We are talking about a rule that everybody has to follow. When we said about 5G, we meant like that not proprietary, but any network implementation can fulfill that rule or meet the requirements of the rule utilizing the existing standard. So we are talking about here, any technology that we discussed today is more of a standardized technology that is either possible to deploy right now, or given the existing developments in standards bodies, is something that one can question whether it can be deployed fairly soon.
A quick yes, no. Are you alluding to a sort of a coexistence assurance process, formalizing something like that?
Right. So if I understood well, yeah, we are saying that the sharing rule needs to be in place, and then it should be in place in such a way that is the assurance that each user of the spectrum can guarantee quality of service. To us, that's the key to enable successful sharing. And what we talked about here is several technologies that we believe can lead to that.
Excellent. Thank you very much for your answer. Appreciate it.
Thank you.
All right. I want to go ahead and say thank you once again to Alex. Thank you all for participating, but I think in respecting everyone's time, we should probably close down the chat. I'll just say as a final note, stay tuned. We'll be offering more chats throughout the summer. And again, we're really excited that Qualcomm is decided to collaborate with SpectrumX, and we look forward to growing that relationship as we go forward here. Thanks all. Bye now.
Thank you.